Yeah, so hello. Uh, Good evening. This is our project element subject. So, we are studying about the purifying photon distribution using quantum interference. So this is an introduction part. For, so let's start it. Uh, Purifying of a photon distribution for photon quantum technology. The generation of the single photon is critical requirement for advancing technology of in photon quantum communication and quantum inference. So basically, how to make photon in this system is basically requirement for today's generation because there is a lot of application for quantum communication and quantum information. So that is the reason we are doing this. Basically, there are multiple ways to like generate photon in photons. Uh, so uh, basically, we use two-state system. Two-level system. There are two energy levels: ground state and second state. Uh, the advantage of this is that uh, this emit only one photon at one time. So that is the reason we are doing this. So there are a lot of like, material and application we are using, they can emit when this crystal photon, but they with some error, like colors entering diamond and uh, organic molecule, trap data, and quantum dots. These are the uh, methods that we can use to generate partially in fields of photons. Okay. One of the key requirements of photon source is the capability to generate highly indistinguishable photons in order to realize non-photon first of photonic quantum technology. Okay. Uh, this explicitly uh, drawn quantum dots can generate highly indistinguishable photons due to the ability to precisely engineer their semiconductor environment. It has recently model quantum interference signed with increasing number of photons. So basically, this is want to say that we get quantum dots by the help of this on the subset we like explicitly grow some layer of semiconductor and then make some quantum dots. By the help of quantum dots, we like uh, we get some like indistinguishable photons. Yeah. Neither of the parts are distinguishable to photon. uh, Central noise mechanism that can cause challenges in the development of emitter-based photonic systems at the scale required in partially for practical applications. In solid state quantum photon differentially arises from both fast and slow critical process. So, like in solid state quantum that we are using quantum dots, the second distinction arises from two essentially arises. There are two processes. The one is fast and second is slow process. In fast process, there is an like electron uh, that can interact with photon when he is excited state. There is some like change in his wavelength. So that is there is the distribution and second is the slow process. When the photon is emitted from the quantum dot, that after that it will connect with like environment formats. So by that reason, like there will be some. So that is the second reason. So by these two reasons, there is photon. On the other hand, slow process such as from interaction and polarization can also affect photon in distribution. So because he want to say that in second process, slow process, like when photon like emitted mm, from the quantum dot that he interact with environment and its polarization of the thing. So any two is a photon is basically like And if we have two photons, then the intensity we call that their wavelength and their arrival time and their polarization are same. So if these three things are same in two photons, then we can say that these are photon are indistinguishable. The, the promising alternative mitigation strategy involves the purification of single photons using linear optical circuits and ancillary photons. Sparrow and Marshall adapts these techniques to purify single distinguishable photons where multiple partially distinguishable photons are processed through quantum interference and linear optical circuit. So basically, in this experiment, we are using a linear optical circuit. Okay, like we uh, like we try to verify the single photon by the help of like two circuits. Okay. So, like in this report, we present an experimental demonstration of linear optical purification of photon in distribution using the solid state quantum dot as a quantum emitter. Between both fast and slow noise contribution to control the partial distribution to emit photons. The photons are then processed using a fiber optical of fiber-based linear interferometer which purified the photons. The indistinguishability of purified photon is arises by simultaneously implemented two copies of purifying circuit and performing quantum interference between the uh, verified output photons. Yeah, so the next part will explain. Okay, so basically, I will explain the quantum interference and the multi-permanent model. So I will explain the theoretical framework we use to analyze the photon interference in linear optical circuit, focusing on the multi-permanent model. So this is a model which is basically a key to understanding experiments such as the Hong-Mandel effect, where we compare the output of an interfering optical circuit and we use a reference configuration in which there is no interference. So our aim is to show that after proper normalization, both the output case and the reference case yield the same permanent for the relevance of matrix. So in this report, this permanent is basically 1 by 4, leading to identical probabilities for both configurations. As a result, the echoing visibility, which is defined as 1 minus P out by P reference, is basically 0. So I will explain that how it happens step by step. So first we define the what is the meaning of the permanent. So the permanent of an invariant matrix is given by this formula. So where Sn is the set of all permutation of the numbers 1 through n, and yeah. So unlike the determinant, the permanent does not include any sign factors. This property makes it very challenging to compute the large matrices, yet it plays a central role in quantum optics. So in this context of boson sampling, for example, the permanent directly determines the probability distribution, uh, probability amplitudes where the identical bosons such as photons interfere in a linear network. So so second, coming to the amplitude for the input-output configuration. So in a linear optical circuit, an input state is basically defined by the quantum states M1, M2, Mn. So these are the different modes. This is transformed by a unitary operation U, which is the transform matrix into an output state in one, N2, and so on. So the probability amplitude is given by the expectation value with respect to the transform matrix, and this is equal to the permanent of B, including these two normalization factors. Uh, and here B is basically the sub matrix of M corresponding to the modes occupied by the input and output. So essentially, the permanent encapsulates all the interference contribution from different paths the photons can take throughout the circuit. So, so now we will discuss what happens for the partially indistinguishable photons. So in this case, the permanent is defined by a 3D tensor W, whose elements are B and S. So B is the B of these two indices. Kj is the element of the submatrix, and B Lj is the complex conjugate, and Sk represents the overlap between the photon states in mode L and K. So generalized permanent of the tensor is computed by summing over all pairs of permutations, which extend the basic concept of permanent to account for partial indistinguishability. So this extension is basically crucial to simulate interference accurately when the photons are not identical. So this the relevance of the multi-permanent model is first of all, it extends the standard permanent calculation to account for partial photon distinguishability. Second, like for the factors like time delay or spectral diffusion and beam speed and norm identities are incorporated into the model. Then, by comparing the interference probability with the reference probability, the model quantifies the impact of interference. And next is quantum error mitigation. That is the understanding and simulating interference helps in designing protocols to mitigate errors in quantum optical experiments. So this is the circuit basically where you can see this is the unitary matrix, which is represented as a black box. So here are the input states with n modes, and these are the output states with n modes. So, and this is the experimental circuit where we have two purifiers and uh, five beam splitters. This is the the last and the final beam splitter uh, where the interference actually occurs. So, so we'll construct this purifier circuit with the help of three matrices, three unitary matrices, where the first matrix corresponds to these first two beam splitters, the second matrix corresponds to this, the next two beam splitters, and the third one corresponds to the final beam splitter. So this is the definition of the matrix. So from the matrix, you can see that in these two corners, we have defined the beam splitters. And in the next matrix, we have defined in the second and third position of the matrix. And in the final beam splitter, uh, for this case, the final beam splitter is in the middle, that is in third and fourth section. So we define the transfer matrix using the product of these three matrices. And so the special case is where we do not use the final one. So in the final one, we use an identity matrix. Next is the submatrix. So next I will explain how to extract the submatrix from the actual matrix, that is the transfer matrix. So, so in both cases, the submatrix from the full transform matrix can correspond to the input state. So the submatrix is constructed by taking the columns and the rows from the transform matrix, which corresponds to the input and the output states. Uh, so after extraction, the proper normalization, the resultant submatrix is such that the permanent basically turns out to be 1 by 4. So next is the uh, HOM visibility. So in this case, so the probability of the configuration in each case is given by the mod of permanent piece whole square. So the P output and P reference turns out to be 1 by 16, and hence the HOM visibility turns out to be 0. So this visibility of 0 means that there is no interference effect. So photons behave as if they are completely indistinguishable. And its classical behavior corresponds that there is a perfect there is a perfect interference. So so now what is the conclusion? So the conclusion is that uh, we define the permanent and showed its importance in calculating interference amplitudes in a linear optical circuit. Next, we constructed our circuit using properly normalized matrices replaced by the identity for the reference case. So after extracting, we calculated the submatrix and the permanent of the submatrix. This led to the output probabilities and the reference probabilities. And finally, the each one visibility turned out to be 0. which indicates that a perfect quantum interference is observed, that is, photons are completely indistinguishable. So, so the next part will be explained by Anime.
So the next part of this project is known as phonon dephasing. So what is phonon dephasing? Let us study what it is and how it occurs. The phonon dephasing is something related to the source itself. So in this experiment, we are generating single photons. We are aiming to generate single photons using a source known as a quantum dot. So quantum dot is basically a solid state system. So in a solid state system, whenever the temperature is anything larger than the 0 Kelvin, then there will be phonons, which are basically quantized lattice vibrations, which will exist within the lattice. So they will obviously interact with the generated pure photons. So when that happens, there will be some phase uncertainty introduced within the generated photons. So as a result, we will not get a single photon wave function, but a wave packet rather. So this wave packet is basically the creation operator for this wave packet is basically defined by this operator AI dagger, which is basically this integral. So this integral contains contributions from all times and then coupled by the convolution operator Fi star of t. So Fi star is basically a normalized function, and it will vary from source to source. For our case, it will be the one due to the quantum dot, and we will see how that turns out. So if we have if we have an AI dagger of this kind, and we also consider whether the computation relations between these different modes, the creation and regulation operators of different modes, AI and HJ, have a delta function dependence, and then this total overall commutation relation at any time for the overall wave packet will turn out to be this integral because the delta functions turn out to be one, integrate up to one. And as we see, this commutator is defined as alpha ij. This will be a definition. And we can readily say that the coincidence probability of two photons, meaning that two photons will actually hit at different detectors at the same time, will be equal to half times 1 minus expectation value of mod alpha ij square. So what is the expectation taken with respect to? Expectation is basically taken with respect to different types of input streams. Right? So this is basically a diagram there describing the phonon dephasing. So as we said, phonon dephasing mainly occurs in any system at solid state system at any temperature, any finite temperature. So when the phonon modes get excited, and then they interact with the outgoing pure photons, the pure photons, and they interact with these phonons, and as a result, the dephasing occurs. So what happens when you pass some kind of wave packet instead of a single photon through single beam splitter? Let us study. So let us consider the different modes that might be possible. So there might be a mode possible one. So one photon in each mode might be possible. Whether they are indistinguishable or not, that is a different question. So if we have this kind of an input mode, we can show that our output consists of states which are determined by this commutator. So these types of commutators have previously already been defined as alpha ij. So it is obvious that this alpha ij term will come when we take the expectation value or the overlap of the states, right? So this will be the coincidence probability. And what we can say is if this is the coincidence probability for photons at two different detectors, then the probability of photon bunching, that is whether the two photons end up at the same detector, it will be just 1 minus this value, which is basically this value. Uh, we can also say one more thing about the indistinguishability of the source photons. So if if the source photons are uh, properly indistinguishable, purely indistinguishable, then PCC will be zero, because this commutator will then turn out to be zero. But the modes are perfectly distinguishable, then this one will turn out to be zero, alpha ij, and then as a result of the PCC will be half. But our input is some kind of in between. So it is neither perfectly distinguishable nor perfectly indistinguishable. What we are trying to achieve through the purification circuit that was discussed earlier is to reduce the magnitude of distinguishability and increase the other thing, the probability of indistinguishability, so that we get perfectly indistinguishable photons. So we pass it through successive beam splitters, wherein the setup is basically described here. So we have a single beam splitter, and then the output of this single beam splitter is coupled with another photon, and then this is done successively. So this is for n equal to 2 photons, and this idea can be extended to n photons in general. So there are some, the main idea behind this purification will be discussed later. So let us now see what the final probability coincidence will be. So this will be the final probability function. So as we can see, it contains two photon terms in general, given the two photons are given as an input. So this is a kind of a conditional probability. And these are the terms which correspond to three photon and four photon correlations. So if we have two photons going through each of the modes, it might happen that we end up with two photons at each of the detectors, or two photons in one detector and one photon in another detector. And that might happen in two ways. And coincidence probability P alpha finally turns out to be this thing. So phonon dephasing is basically a fast process, and here we consider pure phonon dephasing. So we can say that the expectation value turns out to be gamma by gamma plus 2 gamma d, where gamma d is the cube dephasing rate, and gamma is the decay rate of the implant. Okay. So So the basic idea behind coincidence is that we are first starting out with the like initial state, and then we are taking only those occurrences where my output state has and no photons in one detector, which automatically means it has two photons in another detector. So so basically, this will ensure that only bunched photons are passed through, and at last, what I get is basically a indistinguishable state. So let us do some analytical calculations. We can write alpha in a more simpler form for our purposes. We can write this expectation value to be equal to x, which and these approximations are standard, quite standard. We can write the three photon correlation term to be x to the power 3 by 2, and four photon correlation term to be x square. And by automatic substitution, we get p alpha to be this term. So it is a very complicated expression. And so we previously had this term for the two photon thing, wherein we had this more expectation. This is for the raw photon probability, coincidence probability. So this is basically nothing but the overlap of the wave function. So we can define something like this for given my output state of for this probability. So that would be some kind of the mod alpha f square expectation value, which will be defined by 1 minus 2 alpha, which is basically this expression. So what I am basically checking is for a given incident photon probability, uh, what level of purity I am getting. So if this reaches to about 1, that means the photons will be quite indistinguishable, VGF value. So let us check numerically. So using this process, we are checking numerically. So this is an approximate formula which works near x near about 1, but we are using this general formula to plot the graph, and we are seeing that initially this thing outperform the simple indistinguishable model. So if my that would be a straight line, whereas this one has a larger value for some x values corresponding experiments. And thus we see that this pure phonon dephasing model acts as a better assumption in some cases than the simple beam splitting model. For discussing indistinguishability, verification protocol, and experimental setup, I am here. So, in this purification protocol, what we are trying to do is the basic idea is that if two indistinguishable photons enter in a beam splitter, then after interference, uh, in one of the output port, uh, we get two bunched photons, and in the other output get we detect zero state. So in our experiment, we are using for n is equals to 2 state, which means we are only sending two photons in one beam splitter, and after checking their interference, we are obtaining the data whether they are being bunched or not. So for this, we have in this paper they have defined a success probability. Uh, in this case, success probability is such that we detect zero photons in one of the output of the beam splitter, which is attached to a detector. So, uh, if we generalize this case to n beam splitters, let me show you the figures. So, in this figure, this is for n is equals to 2 case. But if we generalize this for copies of this purification circuit, then you can see that the probability of success decreases exponentially, which means uh, that on increasing number of purification circuits, how they get purified, more purified photon, but the probability of getting bunched photons, which are highly indistinguishable, is very less. So we have to optimize between these two probabilities so that we can get a higher rate of indistinguishable photons. So for experimental setup, this is the experimental setup that they are used. It consists of various optical components, such as uh, there are I can name various of them in the series in this they are used. First one is indium arsenic quantum dot, which is attached to a photonic crystal waveguide, and for pumping the quantum dot electron from ground state to higher state, we are using a pulse laser. After that, we have attached an etalon to reduce spectral broadening of the photons. After that, we have used half wave plates and quarter wave plates, which control the polarization of the photons. Then there is this EOM, electro-optical modulator, which is an optical component in which if you apply a voltage, then it changes the diffractive index of the material, so which we can find in the polarization of the incoming photons. After that, there is a like beam splitter, which sends two photons in two different polarizations, namely vertical or horizontal. Then there is this again this polarization half wave plate, quarter wave plate, EOM setup. These are used multiple times so that they can adjust at every instance what kind of polarization we get. So basically, the complete experimental setup can be divided into three broader parts. First one is the four photon source, in which we are generating from a single quantum dots four uh, photon pulses. Then second one is purified circuit, in which the purification of photons are happening, and we are checking that either the photons are indistinguishable or not. And third one is the detection setup, in which we have a superconducting nanowire single photon detectors. This kind of detector uses a superconducting nanowire, which is cooled down to very low temperature of 2 or 4 Kelvin. And if a photon incident on this detector, then it creates a hotspot in that region, which reduces the which increasing the resistance of that region, and through which a voltage drop across the nanowire is measured, and we get a signal that photon is detected. It is very efficient, and its dead time is also very less. So in these kind of setups, these superconducting nanowire single photon detector
often called as SNSPD, is used. Now, if we go one by one, for four photon source, as I said, we are using polarized beam splitter to get two rays from here. Again, we are using two polarized beam splitter such that from each ray we can again get two photon pulses. So at the end, we are getting four photon pulses. You can see there they have used an fiber delay, which compensate the uh, temporal delay that is generated by this path difference of the different pulses that are being uh, uh, coming by the one single quantum dot. So you can see that various light pulses are traveling different paths, which differs their path lengths. So we are adding this fiber delay so that at the output of these four ports, all the photons are coincidence. So moving further, so this single photon quantum dot is generating 938.4 nanometers wavelength of photons. Then after uh, going through echelon filters out the spectral spectral sidebands of photons and gives a bandwidth of 32 gigahertz. Additionally, the pulse laser gets a repetition rate of 80 megahertz, and the detector detects the frequency of 16.1 megahertz, through which we can calculate the efficiency of detector to be 85% of the detection system. Now, moving further, the fourth photon source are incident at the rate of 32 kilohertz. Now, let us suppose there are two photon source incident on purifier 1, and if there are, let's say there is a lot of distinguishability between them. So the purification circuit will do such that the distinguishable part will be reduced and indistinguishable part will be allowed to pass. So after coming through the purifier one, in one of the output ports we can get bunched photons. Similarly, from purification circuit 2, in one of the output port we can get two bunched photons. After that, we are interfering them again such that in the final HOM uh, beam splitter, we can get either bunched photons or either no photons, which we are seeing zero photons. So by checking these systems, by changing various uh, setups that are used in this experiment, which will be discussed in later parts also, in what kind of situations this setup is being used, we have reduced, as my previous group mates have also told, that we have used this from broadly three setups, such as for fast noise, for slow noise, and for different polarizations. So these setups can be used, and from here on, I call Krishi to discuss the results.
So hello. Now, Priyanshu has discussed the experimental setup, and I'll be discussing on how the experiments have been performed and what were the results. Now, there are variations with the experiment that have been done. Now, initially, what happens is that first of all, raw visibility has been obtained. Now, what is visibility? It is some measure of what is the amount of distinguishability the photons have. I mean, if the visibility is very high, the photons are completely indistinguishable, and as the uh, visibility reduces, the photon indistinguishability also decreases. So, what is the experiment that has been found here is, first of all, in the circuit that Priyanshu has explained, what happens that first of all, raw data has been obtained. Now, how is it obtained? First of all, so raw data means without verification. The purifiers are not in the system now. So we have blocked the input number 4 and input number 2 and input number 3, and we have allowed input 1 photon to pass from input 1 and input 4. Now, what happens? We get some sort of output on the detector. So what happens is that we have, so it is being plotted here. Now, it could be seen that initially the counts are very high, as well as, I mean, there is a broad peak around the minima, which shows, and it can also be seen that using some sort of this maximum number of counts and minimum number of counts, we can obtain the visibility. So it is some sort of measure of how good is our indistinguishability. So what happens is that after that, once we have obtained the raw data for visibility, so we want to verify the data. I mean, we want to purify this. I mean, the distinguishability of the photon, and we want uh, the result. So what happens that we can the output 2 and output 3 have also been I mean photons are passing from it also, and further we are going through all these purifier circuits that Kansu has earlier explained, and then we see that the counts have decreased. So we can I mean we can infer here that the counts have decreased. I mean we have taken output from only those. We have considered the probability of successes only. I mean, we have taken the rounds for those photons only in which one of the beams later there is no photon is being obtained. I mean, we can also say that bunching has occurred. So we can see that there is some sort of the minima peak that is being shown. It shows that the width of the peak decreases in case of the verified circuit, and the counts also decrease. We suggest that the I mean the distinguishability has reduced. I mean the photons have become more indistinguishable and the distinguishable component has been reduced. So this was one of the case. Now we performed this experiment in various. I mean by doing various variations. Like first of all, there was no etalon present. So no etalon is present. So there would be a spectral sideband that has been that would be present, and photons may have some sort of slightly different some frequency parameters or intrinsic qualities which would distinguish them from each other. Like it may happen that due to fast processes or slow processes, they may have slightly different wavelength, or due to spectral sidebands or phonon dephasing, which Anil has already mentioned. So what happens is that in case of no ethanol, if we measure the raw visibility data, it will come out to be 0.5829. And when we experimentally measure the purified visibility to come out to be 0.685. We suggest that there is improvement of 10.2% in visibility. We suggest that the indistinguishable component has been suppressed and the photons have become more indistinguishable. I mean, uh, also the peaks also get narrower, and this maximum count reduced, such that the dynamics and amplitude of the distinguishable components are altered. Now it suggests that uh, therefore, now further more experiments were performed. I mean, then we performed the experiment with etalon. What happens is that when etalon is again introduced into the system, that slightly we get restricted wavelengths around 32 gigahertz, which also mentioned amount of photons entering into the system. So there is even less scope of distinguishability between the photons, and as well as there won't be extra spectral sidebands, which would increase the indistinguishability. Increase distinguishability. So what happens that in this case, the visibility of raw data was around 0.90, and after purification, the visibility increased to 0.927. I mean, in this case, the distinguishability is limited. Uh, I mean, because of the noise. And what is this noise coming from? It is because of multi-photon terms that are arising from the multi-photon emission from the quantum dot itself. Now we again found another type of variation. What in this case what they've shown is that in third configuration the etalon is present, but they have slightly detuned the voltage that is applied to the quantum dot. What happens that once the value of voltage that is not the optimal, which is needed, so again suddenly what happens that there may be shift in the energy levels, and hence the photons that are being emitted would be slightly more distinguishable. So what happens is that the raw data becomes 0.83 in the visibility in case of purified data was enhanced, but it was slightly below the case where the etalon was present, as well as the voltage was also optimal. So the visibility was 0.9090, and so in this case, the visibility that we are obtaining, or the amount of purification, that the degree of purification that is being obtained, is somewhat uh, in between that of without etalon case and optimal case. So they have also performed critical calculations, and curves. They have made curves or they have done simulations using the various model like multi-permanent model, minimum purity model, and pure dephasing model that Animic and Ingrid Moore have already mentioned. So these figures can be shown here. So in what this figure suggests is that without it alone, we had, I mean, first let me, I mean, tell about the x-axis and y-axis. The x-axis is V, which is the visibility, raw visibility obtained without the purification circuit, and VF is the visibility that is being obtained after purification circuit is present in the system. So without it alone, around we mentioned around 0.5 to 0.6, and y-axis suggests that what was its visibility after purification. So similarly, they have shown suboptimal and optimal case here, and they have also done some sort of simulation to suggest that what should be the curve pattern of the curve in case of the multi-permanent model, uh, purity model, or pure dephasing model. And so these are the curves that have been obtained, and this I mean this two lines and arrow suggest that what are the purified values. Uh, now this shows our I mean this shows the different data that we obtained, that has been obtained using different experimental tech, I mean variations that were done without it alone, suboptimal and optimal cases. You can see that there is a very small peak here, and we suggest that the amount of visibility that is being increased in case of optimal is the most. And you can also see the width has been decreasing in case of the optimal case a lot. So another type of, now in this case what we did is we will basically purifying the states, I mean that were distinguishable because of the fast processes, I mean fast processes like phonon dephasing and others. Now what we have also shown that we can, I mean, verify the states that are being distinguished by slow error. Slow error, I mean, like spectral diffusion or change in light frequency. So, using that, they have also shown that there is a slightly improvement in the visibility once the purification circuit is introduced into the system, and hence they have shown that. And in conclusion, I would like to say that they have shown that using the, I mean, mitigation technique in order to reduce the degree of, I mean, distinguishability. What they have done, they have shown this type of circuit, and they have found out that both the types of system, I mean, slow process, slow process distinguishability as well as fast process distinguishability could be mitigated. And in this protocol, and they can be integrated into existing photonic quantum architectures. And we could further optimize the purification system by tuning the beam splitters in such a way that by changing or by modulating the reflectivity and transmittivity. So in order to achieve more bunching if you can. So this was basically the conclusion of this paper, and here we have written the code for for a modeling of the theoretical parameters for multi-permanent model, most pure model, phonon dephasing model, and just the results that we obtained by fitting it. And the contribution is that Pankaj Kumar introduced the topic and when one uh, discussed the multi-permanent model, and he came up with phonon dephasing model and theory and graph reproduction. Priyanshu helped us in understanding indistinguishability, purification circuit, and experimental setup. But I have discussed the result and discussion, and I have concluded the paper. Now, this was the paper that we have referred to. Thank you.